because you have two losses, one conduction losses and one switching losses. Conduction losses are independent of switching frequency, whereas switching losses are. So when you switch your diode to MOSFET, vice versa, right? This switching losses that is dependent on the switching frequency matters, because in one cases conduction losses is higher, but the switching loss per switching frequency is lower. So there is a midpoint where either of these solutions may give you a better efficiency, and the switching frequency determines that. So you're looking, let's say, the final answer for you would be like below 50 kilohertz. Option A is more efficient than option B.
Right.
Okay. So I hope in the lab you could see some of the transient responses. Hopefully that clarified some of the doubts you had. Always, calculation of these switching losses are not very straightforward. Showed you like how you can just do it with data sheets, and the book has a much simpler approach, basically with one simple equation, assuming that the dominant losses on the diode or because of the diode. Moving forward, basically we'll see later on that you can actually have different scenarios. So if I want to essentially you have to think about, so you have this MOSFET, you have this diode, okay. So as I mentioned, when you use power MOSFET, this diode is not an external diode, it's a body diode. Okay. So when the power flow from left to right, okay, so your active switch is your S1, and this is your diode. So as we discussed, the switching losses is determined by this diode during turn on instead of this. So in other words, when we look at the losses or the switching waveforms on your active switch or this, what you expect to see is the current is increasing when it turns on, right? And then reaches to your steady state current, right? And then whatever the circuit does, it may go up or it may go down, following the inductor current. But usually this distance or this time is so short compared to your switching. That's why when you look at it as if it's a constant. So this is a current, and there is one assumption that we made that once this commutation is done, the voltage drops. It's not true, as you saw in how I did a little bit more detailed analysis with that data sheet or application note. But again, you can assume that this is current, the voltage will be blocked till the current fully transferred from this switch to the active, and then it goes down almost to zero. So this is sort of switching transient. But now, because this diode, or the body diode, has reverse recovery charge, what happens is when the current reaches to steady state, which basically the current is transferred from this switch to the active, actually there are some charge stored. But that will be added, right, to this side. So if diode is conducted in this direction, and it reaches to zero when it's fully transferred to this, then the charge will be going this way. So the switch current was always like this, power going from this side to the right. So when you see this, it will be added to the switch current. So what you see, the switch current, that it reaches to this steady state, but now it's going up like going up. Right? Going up, then like this. So this portion, this additions, right, coming from this body diode of the diode, right? And now, this time, you have now considered the time that this has been recovered. So now you're switching losses again. As we said, because this is usually the dominant part, we ignore others. And in the book, you have a simple equation, right? And you can calculate the switching losses in MOSFETs. And there is a accompanying diode here. Right? Is that clear? So now, even the first part of the question of homework, you have to didn't actually distinguish or specify the homework. So when you have two switches, right? And I think that's what you guys did in the lab. You have two options to operate this converter, and you want to transfer power from this side to this side. Right? So we identify this switch as an active switch. So when I call this as an active, it means that it requires signals to control. So we definitely add gates to this switch, and control its on and off time. But what about this? You have two options. Because it has an inherent diode, right? You have an inherent diode, you have an option not to switch this. So you can leave it open. In practice, you don't leave it open, but you ground it. Okay, and that's the simplest way of operating the converter. So by knowing the mode of operation, right, you can only switch this and treat this as a simple diode, as if there is no MOSFET. Is that clear? Because it has a body diode.
Well, why would you use it? Like, why would you use the MOSFET and not
No, because as I said, if you know the mode, let's say, actually there's a thing, senior design project, I forgot who has it in this class, that they actually want to specify the mode of operation, like charging and discharging mode, right? So imagine that this is simple logic that, okay, if you are in a charging mode or discharging mode, whatever, let's make this switch as an active, right? And the other way, this guy would be active.
Okay.
So that's one way of operation. So then you always have this reverse recovery all the time because you engage the body diode to its full capacity. But what if, right, you operate them the so-called synchronously, right? So now you put two devices with gates. So when you turn this on, you intentionally send the off signal to this guy, right? And vice versa. So in that case, why engage the body diode? Yes or no? Yeah.
Yeah.
If you look at that basically slide, that diode is only engaged if there is no gate. Because once you create the channel, you actually have a MOSFET. As a majority carrier device. In other words, it doesn't matter if positive or negative, the majority carrier. It's not bipolar like using right? So it doesn't matter left drive or right drive. So in other words, if you operate this connector synchronously, then you don't engage this diode, and now your circuit is different. You only have two MOSFETs. How would you model two MOSFETs? With a constant resistor during runtime, and assuming that you have no reverse recovery losses, there is no losses. If you go with the application that I gave you, you have to consider all capacitance. And if there is no diode, then right? So what is the difference? So if this diode is modeled by a diode, let's say, the dominant losses during conduction, the diode is a voltage drop. How about the MOSFET? Is a channel resistance or a constant voltage drop? Right? How about the losses? So if you pass current, I or I squared. So in other words, then you have a choice. Whether you operate this synchronously, if you know what type of device you're using, right, or not. Because during conduction, right, let's say at high current, right, this is order 1, and this is square. So if R1 is comparable to UV, then definitely, if you don't actually switch on this guy, you have a better performance circuit in terms of conduction. So going back to our question. Imagine that I operate this synchronously. When I turn this on, I turn it off, and vice versa. In other words, I do not have the diode. So you would say that you do not have the reverse recovery of the body diode. Is that true? Or I'm missing something?
I think you're missing that little diode going into the drain of the MOSFET.
No, but in practice, if you remember, right, from previous design, you have a death time, right? You have a shoot-through protection for the death time. So in other words, you want to guarantee that these two switches are never turned on simultaneously. What happens if you turn on these two switches simultaneously?
Short.
What happens?
You have a short.
Exactly.
Yeah.
Right. Do you want to do that? Of course.
No.
Can that happen?
Yeah.
Yeah. Because let's say your PWM is going like this. Okay? You send the complementary to the other one. Okay?
Can you adjust the camera?
How do you want to guarantee that
I
there
think
is
you
no
can hear us.
overlap?
Fine.
You could never stay on the second one.
I guess we're just
So now
SOL.
there is a whole design
It seems that
process
way.
to guarantee that this doesn't happen. Right? You can have it on your software, basically assume that you do not have 100% of switching period available. Or you can actually put the hardware to make sure that when the switch is on, don't turn this on. In other words, in practice, when you have this dead time, which is needed, you engage this diode. So you always have reverse recovery. How much? You don't know. You have to go to the lab and measure. So our first estimate is to assume that you have the full reverse recovery process. You start with the worst case scenario. Any question?
Can you hear us at all? Us online?
I do not hear you. Okay,
Yeah.
now I can hear.
Hello?
Jared, you have a question?
Yeah, you can hear us now? Hello?
I cannot hear you.
So it's like, you're saying that the body diode going into the MOSFET does not have that from chapter 4
Hello? Testing? Testing? Mic check?
when the MOSFET said that.
Nothing?
Which one?
On the
Check. 1, 2. Check. 1, 2.
diode pointing down to the MOSFET.
Uh-huh.
You're saying when the MOSFETs are done, that diode is not done.
Let me just make sure. You're talking about this diode? Okay, I'll explain later. All right. So, do this analysis and go back to this. All right.
Well,
We say that, well,
we are SOL.
maybe I do not want to engage this diode at all. Okay,
I guess
whether
that's
you
good
want
class.
to keep it off
Planning on it. I just didn't get there.
or your dead time
Yeah.
is big enough to engage, this
Makes it hard for me. I work 8 to 5.
So how can I get rid of this time? Right, when it's inherently there. So as you can see in this, the first thing is you have to block the current. Right? So you put this guy, so you block the current from bottom to top passing through this diode. So this diode never engage. Okay? So in order to make it a bidirectional current, because now you don't want your MOSFET operates in the reverse, then you need this anti-parallel diode. Okay? So this anti-parallel diode actually should withstand the voltage from top to bottom. So if you pick a 100-volt MOSFET, this diode is a 100-volt diode. Okay? Yeah. But this particular diode, right? When you apply certain voltage here to be blocked by these switches, let's say 100 volts. Okay? So this 100 volt is blocked by this MOSFET. So this diode only blocks the current, but not block the voltage. In other words, this is a very low voltage diode. Okay? And how would you realize low voltage diode? I mentioned it's not a PIN diode, it's a Schottky diode. Okay? The Schottky diode don't have that drift layer, so you do not have the reverse recovery. So even if it's engaged, right, doesn't have it. So in other words, my symbol, all of them are the same. All of them are diodes. One is body diode, it's not a discrete component. This is a discrete component, but same physics, right? Different characteristics, but same operating principle. But now, of course, you can pick a bad diode. You can put a high voltage PIN diode. But in practice, you would use a 10 volts or 5 volts or 20 volts diode, right? That you can easily find silicon Schottky diode that can be modeled by only a voltage drop. So you still have this voltage drop, right? But switching them, that's the research. And that's what you need to consider in part 2 of the handout. Again, you can go and design it with a PIN and engage all those, reverse recovery, but you don't need to. Any questions? Make this a little bit better. All right. I think now, because we are in a really transition environment now, and most devices now are becoming power MOSFETs, I do not want to take a lot of time on devices electrical output. Because MOSFETs are actually replaced by Schottky diode, but not with silicon. Are it's coming. I don't think you would touch these kind of diodes. Maybe you do, but very high voltage. But go to transportation, space, or data center, you wouldn't. So with that, I want to start. This is very short but important topic. But again, it wasn't very relevant 15 years ago, but now I think it's more and more relevant because it has a lot of implications because of some limitations we have with passive components. So we briefly touched on the concept of the discontinuous conduction mode, but the point that matters here is some devices, let's say that if you just have the diode here, it doesn't allow the current going from top to bottom. So there are situations that these devices, because of these limitations, force the current to go to zero and keep it zero through the next switching cycle. So those were the original, the origin of this mode of operation. And as we'll see, it affects the converter. Again, same switches, same symbols, give you a different characteristics. So I think now this is like a third version of this circuit. The first version, how we derived it from electronics to power electronics. We got the simple D. Conversion ratio of buck converter is D. Then we included non-idealities, then you saw that, well, not anymore D. It depends on R's, so you have more complex related. And now what I'm saying, when you realize these single pole double throw switch with devices with limited capability of voltage currents in a direction, then it affects this conversion ratio. And that's why it's important that we study this. So I want to basically explain this through an example. So I built this simple buck converter. Okay. So by now, I think you guys are familiar because you did your junior design with me. So now you have the MOSFET, you have the diode, you have sources, then you have the load. And don't worry about this part, but I defined my duty cycle with a fixed value at 100 kilohertz. So let's say the initial duty cycle is 0.536, 0.5. So what you expect to see in the output is 28 volts times 0.5, so you expect to see 14 volts. So I run this, and I look at the output. This is my output, so you see it's like 14 and 15. So it's here. This is my inductor current. You can zoom in, right? So it's nice and clean, and this is my output, so it's about 14 volts. Tightly regulated in a way. You can zoom in to see the voltage ripple as well. All right. So this is, I think everyone knows that. So now, what I want you to see here, look at the ripple value. Okay, so the ripple is peak to peak or half. So what we see is like this is like 5.5 and going all the way to 4.5. So you have about 1 ampere peak to peak. And the average maybe is like 4.7 or something. Okay. So when we have a non-zero bias or average going to the inductor, we call this a continuous conduction mode. And that's what we use extensively in our previous lectures. Okay. So now, let me increase the load from 3 ohms, right, to 10 ohms. What do we expect? We expect that the current is decreased, right, because the duty cycle is fixed. So you would see the same voltage in the output, about 14 volts, but now you have 10 amps. So now you expect your current, the bias current, drops from 5 to about 1. Right? So if I zoom in, the voltage remains the same. How about the current? So the current is about 1.5 or something. How about the ripple? I think remains unchanged. Right? Do you agree? So what you see here is by changing the load, the average current changes, but the ripple doesn't. So that's an important fact. So the load doesn't affect your ripple. So the design of a converter is not dependent on the load when you want to pick an inductor. Okay? Of course, if I change the switching frequency, it affects the ripple. If it's longer, it has more time, right, to go up and down, so the ripple is increased. But now we're working with a fixed frequency. Duty cycle effects. Again, longer time, I let this go, the ripple is increasing. So now, let me increase this further. So I go to 15, let's say. So still the same, you see it drops. So I think I can increase this a little bit further so that I reach to 0, and we call that mode boundary conduction mode, or BCM. So in boundary conduction mode, look at this, and the current is so low, right, that it doesn't matter So we can assume it's 0, but you see the ripple is still the same, about 1 amp. Look at the voltage, still no change. So boundary conduction mode is like continuous conduction mode. Let me increase this further, 30. So you expect that again, the bias point goes down a bit more. It looks like we're still in the boundary conduction mode, but we can check. Just put this. Obviously, you see the dynamic has changed. One was faster. So you see now it's really hitting 0, coming back, and I have about 1 amp. So let me just go to 60 volts. Voltage still at 14. All right. So let me see. Maybe that's enough. There we go. Okay, so you see, when the switch is on, right, when you turn on the switch, it goes up. And when it's off, follows decreasing because you have a negative slope, negative voltage across the inductor. It wants to go, but the diode blocks. Diode doesn't allow you to go, right? So here, you have this state that neither the switch nor the diode conducts. Look at the voltage. It's at 18 volts. So previously was at 14 volts, but now you have 18 volts. So why this is important? This is important because your power supply, can have different load profile, right? And may need to operate at no load conditions. What you see here, at no load or low load conditions, the performance or characteristic of this converter is very different than nominal power. So therefore, in converters, one thing that you should basically careful or needs to provide as a spec is the boundary condition. So in other words, you may have to burn some energy to keep this converter working. So perhaps if you design any board or any system or pick any power supplies, small or big, you see that it has a minimum load requirements and you terminate it with a resistor, depending how much power it wants to tolerate, to actually make it adaptable or make it practical for your applications. Because essentially, you have two converters, one at low load and one at nominal. Imagine that you are designing an adapter for Apple and you want regulated 3.3 volts. Okay, so you design it at the nominal power of, let's say, 5 watts. What if you need 1 watts? Right? So you have to then make sure that your converter operates at 1 watt and produce 3.3 volts. So far we only considered the nominal power, which is the most important part. But what I'm saying is at low load conditions or low load or light load conditions, basically the converter may have very different characteristics. And that comes because of the characteristics of the devices that may block the system to go to the other direction. Any question?
Yeah, so what would happen if you put a reactive load? Would the current still be the same?
Well, reactive load would affect the
Right, so what about
Reactive means like I put a only capacitor, or
yeah, like
put
what
a.
about instead of just having R, what about if we have a counter to R plus A, some sort of reactive?
I don't think it works. Let me just put it this way. So let's remove it, right? Because it's the same effect. It's doesn't matter. No resistor or big resistor. So if this is it, I mean, I think, yeah, this cannot work. But you can maybe model this with a very big resistor, let's say.
No, what I mean, what about the load has some real and a reactive?
He's modeling it like removing the resistance.
But why do you have that node? Yeah.
I'm not sure.
Yeah, that node is not useful. That's an extra. The only reason that you would need that sort of a impedance network if you want to create a resonance, right? So you want to use the peak, like the previous, this fluorescent lamp. Some of them operate based on this, resonance circuit. So actually they use a buck converter. It's very simple, actually exactly the same circuit, just assuming that this is like H bridge or half bridge, and they put midpoint on the DC side. The way that you design the L and C is for ripple. Okay? So if you go down designing of those and their interaction, L and C are far from the resonant frequency, LC omega square, is far, far, far from the switching frequency, that omega. If that omega, or the resonant frequency, is close to the switching frequency, and if you do not have any active load, then your buck converter behaves like a boost converter. It shoots up. So there are some applications, but here is this.
But because the reactive element will introduce 90 degrees of phase shift to the current.
Both of them, it's a zero. So impedance is zero. So basically you produce zero voltage. But can you produce zero voltage from a non-zero voltage? No. So the way the resonance works, you create humongous voltage, I would say, right? But 180 degrees together. So when you add them, it's zero. But when you measure this load, it's a huge voltage.
Okay, thank you.
Maybe I was a little bit crazy, but 5 years ago, that was my junior design in the lab. So we were making 400 to 800 volts with 20 volt or 40 volt supply. Anyways, so here, what I wanted to show you here is with this continuous conduction mode, essentially you have 3 sub-circuits. You still need to write down the volt-second balance. Volt-second balance, charge balance are exactly the same. But now instead of having 2 sub-circuits, now you have 3 sub-circuits. In the first sub-circuit, the switch at position 1, or the active switch conducts. In the second sub-interval, the diode or the switch at position 2. And you have a third sub-interval that none of them conducts. There is no current in the circuit. Yeah.
And so discontinuous mode is the result of overloading the power converter.
Don't get me wrong. So this is starting. We want to start analyzing this, and I'm just explaining you like when this may happen. So I'm saying that any converter during light load, it may go to discontinuous conduction mode, and you would have a different converter. Now you would ask, can I design a converter that solely operates in discontinuous conduction mode, or operates only in continuous conduction mode with the defined boundaries? So what are the other parameters that affects this? So many things. Load, inductor value, switching frequency, right? That's it. And therefore, because it's a combination of these, we define a parameter that we call it the tendency of the converter to operate in DCM or CCM. It's a very qualitative term because it doesn't depend only on one parameter. Yes, please.
I was going to ask, in a synchronous motor, could you have two separate
Yeah.
Okay.
Yeah. You have to actually.
Okay.
Yeah. So why would I do that? Why should I operate the converter in DCM? Any guess?
I think I've heard before that it can be more efficient. Is that true?
Why is more efficient?
I don't know. I've just heard that.
Okay.
I mean, I assume because there's a point where you're not using losses across the switches.
Uh-huh.
Because at that point, no.
So when the current hits zero, the other switch starts at zero. Do we have any switching losses when a switch or a diode starts from zero?
No, yeah, that makes sense.
No.
Or at least a
Right?
lot. Yeah.
So therefore, it has a huge advantage in basically a highly efficient converter, right? To operate at DCM or BCM, which is boundary conduction mode. The challenge is how to get there. Sometimes we actually use a variable switching frequency to adjust so that it reaches zero and then you switch. And we call that zero switching or zero current or zero voltage switching. And those type of converters in power electronics or this kind of switching is called soft switching versus hard switching. All right. What is the other advantage of soft switching or switching at zero?
I mean, I guess that if the circuit is
Soft
disconnected,
switching meaning that you start or stop the switching action at either voltage, zero voltage or zero current. In a DCM, some switches are operating at zero current for sure.
So we saw in the lab that they would just talk about efficiency.
The efficiency, yeah, for sure.
When they both switch at the same time.
Well, it's a power loss. Yeah.
Okay, you're asking now for another advantage?
Yeah, another advantage. Have you heard about EMI?
Yeah.
Right?
No.
So EMI noises occurs because of the switching at non-zero current.
Okay.
So if the switches essentially switch at zero current, essentially you have zero noises. And in industry, in modern industry, it's called silent converters. Okay, what are the other advantages? What is the design parameter that gives you, as a designer, to, let's say, operate this converter in a DCM? What components may be affected by this? So let me put it this way. Do you need a bigger inductor or a smaller inductor to have higher probability to operate in DCM?
I would think so.
In other words, if you want to operate the converter in DCM, do you need bigger or smaller inductors?
I would think smaller.
Yeah, exactly, right? Smaller. Okay. So if you operate the converter in this continuous conduction mode, and you would need smaller inductor, do you see any advantage?
Smaller inductors are cheaper and smaller.
Cheaper space, right? So there are a lot of things, right? That, you know, when you realize the switch, the converter will behave in a certain way. So it's not all advantages. I mean, because it's very difficult now to have, you know, zero switching. So for instance, here it's zero switching, but during peak you have non-zero switching. So it's not entirely true, right?
Yeah.
So the impact of DCM is when you have an active device with substantial losses, let's say during recovery, for instance, if you have DCM, there is no recovery losses shown up. And it's more complex. Later on, we see that the control is also less, I mean, none of them are complex, but it's a little bit more robust. But definitely the characteristic is different. It's a bug, but it's different. So what is it? So you have to know how to analyze this type of converters. So again, I'm going back. I reached to a point that I saw I have a mode of operation that affects my performance. So I had to know it. But at the same time, once I understood, I see how I can use it. So it's a two different approach, right? One is analysis, and the other is design tool. So I think I explained it here. So if you have this buck converter, you have certain ripple. That ripple depends on input, output, and inductance value, and the switching frequency. If you reduce, you know, the power, the bias point drops, but the ripple remains unchanged. So the ripple is not dependent on the load. If you go further down or reduce the load current, then you would see this type of, you know, behavior, that you have now 3 subintervals. So when you say this, that, okay, can I define a condition or criteria that I can use to define whether the converter is CCM or DCM? And that's when you can, I think the first homework, I intentionally put that in basically with a simple triangle, right? But now knowing how the load and ripple value changes, you see that whenever the load current is greater than the ripple, your converter is always in the CCM. And when the load current is smaller, you are in a DCM. So now, depending on what type of converter you have, you can find a relationship for the average current in the inductor and the ripple, and see, you know, if you can find any parameter that you can extend to all kind of converters. That's not needed, but for basic converter is possible. So for a simple buck converter, load current is the average value of the load current is the inductor current. So you have output voltage divided by R, nothing else than dVg times R. So you assume that the converter operates in BCM with boundary conduction, so you can use all the CCM relationships. And you can put the relationship for the ripple that we calculated based on one of the subintervals. So let's say this. So if you do this, right, do some arrangement, what you get is this form. So you see 2L divided by RTS. And that's the unique parameter that you can extract from all basic converters. And this depends on you how you want to operate this converter, the control. So this is physical components, this is control. So 2L over RTS, the tendency of the converter to operate in this continuous conduction mode. And for only the buck converter, K, right, or the critical value for the K is D prime. For boost converter is different. For buck boost is different. So now what you say is, whenever this K, 2L over RTS, is less than D prime in your circuit, your converter is in DC. And when it's higher, you are in CCM. So again, imagine that you design your converter. So you know your L, R is defined by the load, that's a spec, that's a nominal load, and now it's a range. TS is a switching frequency that you already fixed. Okay, this device is, let's say, good initially at 100 kilohertz. So as you can see, this is fixed. And now D prime also fixed because it's CCM, right? If you have 20 volts and the output you want 10 volts, then D prime is 50%, 0.5. So now you just calculate this 2 times L, whatever you calculated or had initially, divided by nominal R times TS. If it's smaller than 0.5, then your converter operates in DCM. If it's greater, it's in CCM. Is that clear?
And that expresses some larger resistance.
Exactly. Yeah,
Okay.
that's correct. As I said, you never design it like equal or something, right? That's why it's called tendency. So the smaller it is, you're deeper into DC. The bigger it is, you are very far. We call it deep CC. Yeah, exactly. So in other words, when you select your components and conditions, this K is fixed. This K is fixed. For the buck converter, K critical is D prime, 1 minus D. Okay? So if you have a converter, this is D prime, or 1 minus D line, 0 to 1. If the K is here, right? K is now is a number, right? L, let's say 10 micro, Henry, R is 2 ohm, TS is 10 microseconds, whatever, right? So now, if it hits somewhere here, for the D, this side, you see, this is greater than this. So you are in DCM, K is always smaller than K critical. You are in DCM. More than that, you are in CCM. If the K value, based on the parameter that you've chosen, is always greater than 1, right? Imagine K is 10 now. K is always greater than 1. Then your converter is always in CCM. Because you can set that K can be variable at the design stage. L, you have freedom to choose what L. TS, you have the freedom. But once set, imagine you're dealing with a fixed frequency converter, then it's constant. But now R is changing. You never expect to have a fixed load all the time. So, smaller load, light load means bigger resistance. Bigger resistance is coming down. So in other words, you really have to think about how to define the converter, right? And in this case, non-idealities of some of the components helps you because there's leakage current, resistance, leakage resistance, and everything that draws current. That actually helps to operate the converter during lifetime. Okay. So you can calculate this for basic converters, right? As I said, the condition is when the average current in the inductor is greater than the ripple current, you are in CCM. Then find the value, relate the I, the current, with input-output characteristics, the parameters, and delta I the same way. So if you do that, you can find the critical value for the buck, D prime. This is for the boost, and this is for the buck boost. Any question? So how should I analyze the converter? Well, you just have one principle, two principles actually, right, that you want to use throughout this semester. As I said, now you have three subintervals. Okay, so in the first subinterval, you have input voltage minus output voltage across there's a voltage across the inductor. The current in the capacitor is the inductor current minus the load. In the second subinterval, like before, voltage is minus output voltage, and inductor current is again divided between capacitor and the resistor. In the third subinterval now, basically there is no voltage across the inductor, there is no current, none of the switches conduct, and the capacitor current equals to negative load current. All right? Again, you have inductors and capacitor, so you should have inductor volt-second balance. So for the first subinterval, you have D1 or D, you control the first switch, VG minus V. For the second, you have D2 minus V, and for the D3 or the third subintervals, there was no voltage across the inductor, so it's zero. So in this situation, D1 is known. D1 is your main unicycle, but D2 is unknown. Previously, you had D and D prime. So once you set the D prime was complementary to D, so you had 1 minus D. But now, you don't control this part. This is defined by your circuit. So when you look at this, essentially D1 is your main duty cycle or D, but D2 is unknown. So you need to consider more equations to find the relationship between input and output. So when one of the principles doesn't help, you just go for the next one, charge balance. So you look at the capacitor here, right? Like before, the capacitor current is inductor current minus the load current, right? So here, what you would say is, regardless what this capacitor doesn't carry the current all the time, it's a filter. So the average inductor current is essentially the load current. So that's one thing, okay? And this is your, inductor current, right? So the inductor current is going up, going down, now hit 0, and for the third subintervals, it doesn't conduct anything. So you just calculate the average value of this waveform, and this is nothing else but the load current. So to calculate this average, right, you need to know the peak value, right, and you need the base, which is D1 plus D2. So using this equation, now you can use D2, and now you have a set of equations with D2. So you substitute D2, or you find D2 from one and substitute in the other equation, and boom. You now have the relationship that relates input to output. So that equation is this, right? So what you have is average value is the load current is V over R, right? Base is D1 plus D2, okay? So you have D1 plus D2. Oh, okay. And then the height or the peak value is, because start from 0, you can just use this side to calculate the I peak, right? So I peak is L di dt, right? So the voltage is Vg minus V divided by L in the first subinterval here, right? So that's the slope. So that's your I peak, and you just substitute it here. So you have one equation here, another equation there. So you just substitute and you simplify and you get to this equation. Well, again, it gets even more complicated. Okay? As you can see, now, like non-ideal converters, the characteristics of a converter under this continuous conduction mode that I simply showed by simulation, now you have the relationship that depends on circuit parameters other than duty cycle. Now, L, load, and switching frequency affects the characteristics. And with the K term that we defined, now we can simplify this. So keep in mind that this is only valid for discontinuous conduction mode. So in other words, if K, right, the actual 2L/R RTS is greater than K critical for this type of converter, then this is not valid. So this is only valid for discontinuous conduction. And this is like the characteristic. So if the K greater than 1, talk about it, you're always in PCM. So it's a buck converter, V, right? But when K is less than 1, you have different characteristics. So by defining the K, as I said, because it's not variable in a way, you choose how many points and what is the load range, then you get different characteristics. So in order to be regulated, you want to have the minimum variations over a good range of loads, or you need to define. So this is, the characteristics. So you can do that for other converters, exactly the same. Any questions? All right. So I think by this one now I completed, these non-idealities and, DCM. As I said, it's very important, especially boundary conduction mode. So the homework for this one, because we have a delay on the previous one, will be make it available, but we'll do it March 1st. So 2 Tuesdays from now. Any question? All right.
Yeah, I was wondering, so the midterm exam, what chapters? 1 to 6?
1, 2,
I mean, 2 to 6?
1, 2, 3, 5, right? 1 to 5.
5?
Yeah.
So we're gonna do 2, 3, 4, 5.
Yeah.
Recording stopped.
Right after the break.